Well, my name's Jim Duey, and I'm talking about DSLs in Clojure. A couple of caveats to start off. This talk is really supposed to be much longer, and so there are a lot of slides. I left them in here so that you'll have them online when you go look at them, but I'm going to burn through some of them, and so just expect that. And so with that, let's get started. In the dawn of computing, you had the hardware. Then they added machine language to program it, which was just raw numbers. Then they added assembly language, which put mnemonics associated with the opcodes. Then they came up with subroutines because they saw strings of instructions being repeated. And then they came up with higher level languages to make it a little more descriptive instead of working with assembly language. Then they came up with block structure programming to get rid of the gotos, which was quite a interesting time. And then object-oriented programming. So each of these layers of abstraction hid something of the layer below it. This is all on the imperative side. And the functional side, you had Lisp. Lisp was pretty much the end-all, be-all of programming languages, as far as I'm concerned. But then there was room for Haskell to come in. So the question is, what's the next abstraction layer that lets us take the next step, lets us write more code or do more things with less code or the same amount of code? And I think a good candidate for that next abstraction tool is domain-specific languages. And hopefully this talk will kind of tell you why. There's been some buzz over the past, 10 years or so or more about DSLs. Paul Graham, that's a paraphrase, that's not a direct quote. Alan Kay, I highly encourage you to get the VPRI 2011 annual report and read it. It is not your typical annual report. And he comes the closest to the ideal of what I want to see in terms of using DSLs all over the place. Highly recommend reading that report. Simon Peyton-Jones, obviously, did Haskell. Has some videos that he talks about using Haskell to write DSLs and how great Haskell is for writing DSLs. Martin Fowler wrote a book in 2010, and that book mostly focuses, or is limited, he says explicitly, it's limited to object-oriented programming for doing the DSLs. And it's also focused on using DSLs for the end user, and I was more interested in how I, as a programmer, can use DSLs to make my life better. Also in 2010, Terence Parr did Language Implementation Patterns, which is a very good book, talking about lexers and parsers and the like. And then Debasish Ghosh, I think I got his name close to right, wrote this book also in 2010. It was a good year for DSL books. And of the three, I would recommend this book because he covers both OOP and FP and does a multitude of languages, and really nails some of the concepts of DSLs. So I would recommend this book over the other two. But what I wanted was a methodology for writing a DSL. Because I wanted to apply DSLs in more than one place. I didn't want to just write a DSL for the end user for somebody else to use. I wanted DSLs to help me write my code better. So think about writing software. You start off with a set of requirements. And as you have those requirements, you look at them, you start thinking about the solution. You start envisioning the way the solution is going to look. That encompasses the requirements. And then, like the very next step, is to break those requirements up into smaller problems that have their own set of requirements. And you keep doing that. You keep breaking these pieces down, these problems down into smaller ones. And then you start solving those smaller problems. And as you solve these small problems, you start composing those small solutions into bigger solutions. Until finally, you can compose all those solutions into your final solution. And that's the way, it's second nature. If you program, that's just the way you do it. But in all the years I've done programming, there was a question that was unasked that I never really asked or thought about until I started thinking about DSLs. That question was, how do I put these things back together? I just assumed that I was going to use whatever language I was working in to wire the function calls up together and make it all work. And so until I started thinking about this, I never really thought about that question of how to actually compose these pieces of solution. If you look at it in a different way, your main solution is composed, in this case, of another layer that has 3 solutions in it, 3 sub-solutions, you might say. And each of those are composed of, smaller solutions. And so there's like a layer of composition or a layer of abstraction in your building up to your main solution. And what I am here to talk about is at each layer of composition, that is an opportunity to use a DSL, in my mind. And that DSL hides the mechanics of composing these pieces and lets you just write the solution. Lets you write the ideal way of writing that solution so that it communicates that solution to the people who are reading your code. And in this case, there are 3 DSLs. Each box would be where a DSL would be used. So you can see the pink and the blue kind of do those compositions on those layers. But the green one spans multiple layers. And that, I think that's perfectly acceptable. Another way to look at it is you can use the same DSL in totally different parts of your solution, of the code that you're writing. So you use the same DSL over here and the same and over here with no real connection between the code except they both use the same DSL. So let's take a look at some real DSLs real quick. Compojure. I hope you guys are mostly familiar with it. A very good library for composing HTTP routes to handlers. There is an operator that does these compositions, that mashes all these routes together. It's called routes. What this library, or the DSL, hides is the mechanics. All you have to do is declare the route and the handler function, and it does all the mechanics of matching up a HTTP request to that handler. That's what some sample Compojure stuff looks like. All right, Korma. Chris Granger did that. I've gotten a lot of mileage out of Korma. It lets me avoid writing a bunch of nasty SQL. So what it's composing are parts of queries that you can build. You can build each part using the where or aggregate, and there are some other things. The operator that composes these is Clojure's threading macro, which is kind of hidden in the select function or the select macro. But that's what basically is doing the composition. And what this DSL hides is all the nastiness of building building up in a huge SQL expression. It hides that by letting you decompose that. And then there's the select function. And that's what some Korma looks like. And that's some more Korma. Except this slide's a little out of date. Chris has informed me that the exec function is no longer necessary. I haven't looked at that, so I'm not sure exactly what he's talking about. core.logic. David Nolan. It composes relations that are built or created using the unify operator, which is equal. The operators to compose relations are these guys. And what this hides, what core.logic hides, is the backtracking. It lets you, and passing substitutions around. And I won't go into all that details. But just know that it's hiding a lot of nasty mechanics underneath there. And then run is how you use it. So this is the most important slide of the talk. What's the process of actually coming up with a DSL? First of all, you take your problem and you decompose it and break it up into smaller problems. And then decide exactly, in the ideal world, what it would take to write the composition of these smaller problems. And when you have that ideal syntax, so to speak, then that is kind of what your DSL is going to be. So you decide what you want to say. How do you want to compose the pieces of your solution so that it communicates as clearly as possible what the solution actually is without getting bogged down in a lot of the junk that are necessary, the mechanics of doing the composition. And so in deciding that, you decide what you want to compose. What are the so-called primitives of this DSL? And then the other question is, how are you going to compose them? What are the operators that you're going to want to compose these primitives? And then really important is, what do you want to hide? Because in my view, looking at DSLs in this lens, they're an abstraction tool. And abstractions are for hiding things, for hiding complexity. And so decide what you want to hide. What is the stuff that's incidental to your solution, and hide that. And let the essential complexity, stand on its own and be visible all by its own without any of the incidental stuff clouding up the text. And then what are the boundaries and interfaces? So as you're reading through your code, how do you know when you cross into this DSL? That's the concept of the run function in the previous slides. And so Richard Gabriel yesterday, he talked about how languages are used for communicating. That was kind of even a side comment. And that's really what DSLs are for. They are for communicating, so that when you come back to the code later, you can read your solution without having to play compiler and say, okay, well, this function gets called with this and this and this and blah, blah, blah. You can just read your solution. And that's how I envision DSLs being used as a programmer to help me write code. So some rules of thumb. This is like the second most important slide in the talk. Don't implement a general purpose language. They're called domain-specific languages for a reason. You don't want to be Turing complete. You want them to only do what you want them to do for the problem at hand. And so as part of that, you keep the operators to a minimum. Each operator that you introduce into your language is a different concept. And the fewer concepts you have to mentally think about as you're reading this language, the better, the less cognitive load it takes. And so keep your operators to a minimum. Use the operators that you need, but no more than that. And then another very important point is to make operators return the same thing that the primitives are, the same kind of thing. And what that means is you take an operator, you do an operation on some primitives, and you produce something. That something should be able to be fed back into the operator as a parameter. And that lets you factor out commonality and then be able to assign those results to a symbol. So you can name that piece of common functionality. You can put a name on a descriptive name that then makes sense when you use that in a composition later on. And then leverage your host language. That's why I love DSLs and Clojure, because you have macros, you have a simple syntax with S expressions. So leverage your host language. Don't try to do something in your DSL that's already in your host language. So make use of your host language, in this case Clojure. Alrighty, how does this work in practice? So this is a DSL to test ring handlers. And this is the ideal. If I wanted to test a ring handler, this is the ideal of how I'd want to do it. I'd want to make a script that did a request, then tested, did some tests if the return code is 200, if the body contains a string. That's how I would want to write it. So what are the requirements of doing that? First, request and test are types of actions, just generically, and actions compose sequentially. So you have a request, then you have test, 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 then you have another request, and then test, test, test. So it's a sequential composition. And you need to pass the response. So you get a request, you do a request, you get a response back. You need to pass that response through the successive tests. You also need to deal with cookies from one request to the other. So you do a request, you get a response, take the cookies out of that, and submit those cookies on the next request. So how do you do that? How do you implement that? If anybody has read anything I've written on the web, using the state monad should come as no surprise. It lets you handle that state that you're passing through very easily, very cleanly. And it hides all the details of actually passing the state through. And then if you do that, actions just become monadic values under the state monad, which means to say they're just functions. So the actions are just functions that take a state, return a value, and a new state as a vector. And script, the sequential composition of these actions, is just the mseq function underneath the state monad. which it also produces monadic values, the functions, that can then be plugged into scripts. So you can take a piece of common functionality out of one script, factor it out, put a name on it, and then throw that name into an additional script to use that functionality repeatedly, because it can be assigned to values or symbols. Another requirement, you want to abort when a test fails. So you do a request, you do test, that test fails. You want to stop the processing at that point. The baby monad is perfect for that. So to combine those two monads, you need a monad transformer. And if you guys didn't hear Karen's talk, go back and listen to it. She'll explain a lot of this stuff. So implementation. That is just the script monad. That's how easy it is to build. A little bit of syntactic sugar to cover up some of the clumsiness. And then script. It just is the mseek function. That's the request method. And I won't go over it line by line, but it basically just builds a request map, sends that off to the handler, gets the response back, and adds that response to the state that's being passed along underneath the covers. This is how you write a test using this monadic value. You just get the response out of the state that's being passed. That's what the get val : response is. And check to see if the body of it contains the string that's passed in as the test parameter. Likewise, the response code. Get the response, see if the code is equal to the code that's being passed in. Set cookies, I'll just skip over that. That's the function to run a script against a handler. It just builds an initial state, very simple with that hash map, and then runs a script on it, extracts the value out, and turns it into a Boolean, so that your the result of your test becomes true, false. True if it passes, false if it failed. But with that implementation, you can write this exactly. You can write the ideal, and that's I don't want you to get so much bogged down into the actual implementation of it using monads and whatever, but writing that DSL, implementing that DSL, lets me write exactly the ideal of what I wanted to write to efficiently test ring handlers. And you can read that, and you can just see, okay, I do a request on the root route. Does the return code equal 200? Does the body contain some string? Then I do another request on the illegal route. Is that return code 404? You just read it. There's not a whole lot of thinking you have to do to make sure that this is the right thing. The usage, I'm going to skip all the stuff. You can go back and read it. Basically, I just define a simple ring handler with a couple of routes in it. Define a test script, a couple of sample test scripts, factor out some commonality code with the hit counter, and then use that hit counter to build a larger script. So, I wanted to get to this point because this is kind of a philosophical part of the talk. As programmers, I want to write good code. I want to write code that does really cool stuff. I don't want to get bogged down in, do I have the right data structure? I mean, I don't want to get bogged down in the details of, okay, do I use map here? Do I use mapcat? Do I use filter? Whatever. I have to answer those questions. I have to do that implementation. But when I actually express the solution to my problem, I want that solution to be beautiful. I want it to look good. I want it to be elegant. I don't want to have to look at the minutia of the implementation. And I was actually kind of influenced in that view by looking at Richard Gabriel's website, and he talks about beautiful code. And Jim Copleen, I think Copleen, did a talk, and he talked about the architecture and Alexandrian forms, and I don't understand nuts about that. But the idea that came through that, the philosophy that came through that, is writing beautiful code. And code should be like poetry. You should be able to read it and see concepts that pop up without having to play compiler without having to step through vast expressions of code and say, well, this function does this, and then this, and this, and this, and then this gets passed around and all that stuff. You should be able to just read the solution, read the text of your solution, and have it mean something. Have it not be ugly. And so that's really the point that I want people to use. I want people to do is to write good code that you can look at and have a good sense that it actually works. And Bradford mentioned it this morning about how flop 180 lines and this other thing 180 lines. I mean, that's good. And so all of these, that's why I think domain-specific languages are the next layer of abstraction, the next tool of abstraction. And you can pick any part of this tower to work at. You can work at any level of abstraction. And I'm of the mind, and in my code now, when I come to a problem, I'm thinking in terms of DSLs. What do I need to do to create a DSL to solve this little piece of my problem? And then what DSL do I need to write to compose that piece with this other piece that I did? And how can I make that look as clean and as elegant as possible and strip out all of the extraneous stuff that you need, stuff that's necessary, but how can I hide that? And so that's my take on why DSLs are good and how to use them as a programmer. I have a blog that I develop these ideas a lot more fully on, Clojure.net. Should be easy to remember. Twitter, that's my handle. So I tweet about these kinds of things. And then the code for this script DSL is there on GitHub. So, and with that, any questions? Actually, the blog, Clojure.net, is this in-depth. It starts off with a monad tutorial for several posts and then moves into DSLs, and it is this talk at a much deeper or a much more verbose style. So actually, if you read that talk, you wouldn't have had to come here. Or if you read that blog, you wouldn't have had to come here to hear me. But I highly recommend Alan Kay. Let me go back to that slide. VPRI is doing this. Their goal, their stated goal, is to write all of the code of a computer system, an operating system, from the metal to the user in 20,000 lines of code. And that's everything. That's the networking stack, that's the email, that's the PDF renderers, that's everything. 20,000 lines of code. And the way they're doing that is they're using DSLs to hide the complexity. They do an entire rendering language in 80 lines of code. So get the annual report, read it. It's just awesome. And then that video, Programming and Scaling, do a search for that and find it. Because he talks about, it's like my inspiration for this. So basically, I stole his ideas. Actually, in that GitHub repo, I just pushed another DSL as part of that repo to build dynamic web forms, or web forms that are backed by a database table. And so it lets you descriptively describe your form in the HTML layout and insert fields that are actually backed by a DSL table. And I'm in the process of writing some blog posts. I posted one yesterday that described that DSL. So really, whenever you have a layer of abstraction that you need to compose things, that's an opportunity to use a DSL. And in my thinking, what I've come around to is I can create a DSL for each different piece of my project. It's like using objects, is to use DSLs like you would objects. You think of the way you decompose your problem using objects. Decompose your problem in terms of DSLs. Does that answer your question? Thank you, guys.